There is a legal theory, small here for contract theory. I see options as contract theory. So I tried to connect them, and this is available on the web. Okay, that's the Incerto project. So volume 5 will be around this symmetry, where you're an option trader. You understand asymmetries. I own an option, you short an option. Okay, I have unlimited upside, you have unlimited downside, but I have limited downside. You see, and you have limited upside. So this is pure legal theory, except mathematized. So try to connect these, and the next one is skin in the game, the next volume. And they're all the same story, how to live in a world that has a structure of uncertainty that's too complicated for us, and certainly too complicated for statistician, mathematician, philosophers. So that's the Incerto project. Okay, it keeps going, keep adding volumes, and if I ever become better at chess or bridge, maybe I'll stop, okay? And there's some technical papers. Now let me explain the notion of fat tails, how it relates to extremes, with that notion, that distinction between mediocristan and extremistan, or the two domains that are very separate. Randomly select two people from the UK, and assume that you're locked out, you got a tail event, a total of 4.1 meters, 410 centimeters. What's the most likely combination you're going to get? 4 meters and 10 centimeters? No, what's the most likely combination? Conditional on having 4.1 centimeters as a total for two people. The probability of exceeding 3 sigmas is something like 1.35%. The probability of exceeding 6 sigmas, which is twice as much, is of the order of 10 to the minus 10. And so the probability of having 2 times an event of 3 sigma is something of the order of 10 to the minus 6. It's considerably higher than the probability of having 1 times 6 sigma. So 2 3 sigma events, as unlikely as it is, happens 1 in a million approximately, is vastly more likely than having 1 times 6 sigma, okay? And that's a definition of that class of distribution that is not fat-tailed. And we're going to see the logic. And the graph here shows you, okay, as you extend the sigmas, as we're looking at the ratio of 2 events, say of 3 versus divided by 1 event of 6, 2 events of 5 divided by 1 event of 10, and look. So the more you go into the tail, the more you realize that a large deviation can only occur via a combination of a lot of intermediate deviations. You see? That's the logic of what we call mediocristan. Let's go further here. So this will explain the difference, because let us assume now that you randomly select 2 people, and their combined wealth is $36 million. I don't know the exchange rate today, but assume, okay. What's the most likely combination? 18 million and 18 million? No. What's the most likely combination? Very approximately, say $1,000 and 36 million minus 1,000, right? Okay, so here, so you see the difference between the two domains is very crisp. Okay, so now we have pretty much, now the mass is to the right, ignore it, unless you're a mathematician, okay? This is the legal disclaimer here on the right, okay? So you don't get annoyed with what's on the left, which is actually sufficient for most people, including mathematicians. The catastrophe principle, for a class of sub-exponential distribution, ruin is more likely to come from a single extreme event than a series of bad episodes. That's it. So in the domain, the second domain, like wealth, if I say that, if someone tells you the net worth of this room is £1 billion, okay, you know that can't come from each person here having a net worth of £15 million. It's much more likely to come from, it's a tail event from someone with a, with a net worth of £1 billion who just happened to visit, okay? So, and if you follow this logic, Now we follow this logically, okay? Simple, logically. It's going to take us quite far, okay? Let's start with classical risk theory, where this was born. Kramer, 1903, 1930, actually it's Lundberg, and then Kramer formalized it. That basically, insurance can only work in Mediocristan. You'll never have today, except for someone who worked for Lloyd's of London and didn't understand the problem. And Lloyd's of London, I'm talking about, was a name for Lloyd's in the 60s, 70s, and 80s. You never have an insurance contract that's uncapped for that reason. So catastrophe. So this was understood long time ago, and of course people forget about it. So now let's define fat tails formally. Okay, or more formally with more intuitively for all of us. Okay, fat tail distribution are one in which extreme events, the ones away from the center of the distribution, play a very large role. That's it. It is not as when people start talking about black swans, they say black swans are more frequent. No, they're not more frequent. They're more consequential. The fattest tail distribution is one in which you'd have one very large extreme deviation, you see, not many departures from the norm. And if I take a distribution like the Gaussian and start fattening it, you notice that effectively the number of the departures away from one standard deviation drop. So let's take a Gaussian. What's the probability of a Gaussian staying between -1 and +1 sigma? 68%. If I fatten the tails, what happens to that number? In other words, we have 15% probability exceeding, 15.6% probability exceeding 1 sigma, or 15% to be below 1 sigma, okay? What happens if I fatten the tails? No, it goes up. The probability of staying in the middle goes up. If you take financial markets, it's somewhere between 75 and 95%, between -1 and +1 sigma. Incidentally, sigma has no meaning with fat tails. But you stay, because you have fewer departures, you have higher peaks. And this is what happens. You have higher peaks when you fatten the tails. Higher peaks, higher incidence of very large deviation, and smaller shoulders. Okay? For net departures away from 1 sigma to drop in frequency.